Okay, last Friday I covered quite a bit. I covered almost all, except some experiment performed in the past by the bandettes, whoever. That portion I'm gonna cover today. But I'm going to briefly review. I made up the full problem. You will get the full problem set. I could do close the book because you don't have to flip all my notes. You really need all you need maybe a notes, my notes. Oh, you may not need any. You can just do it without looking at any equations, relations that much. But what we covered, this is relevant to the final. What we covered was, except the Friday lecture, is all input, output, and system relevant to problem we solve. Once you solve the input, output, and h function or small h function, if you do that, if you can maneuver very well for multiple input, multiple output, is very easy. But if you don't know how to handle single input, single output, including noise, then you are in trouble. So it's the same situation in the vibration theory. You have to know 100% right for solving the single degree of a freedom system. Then multiple degrees of freedom system is a piece of cake. When you make a modal transformation for multiple degrees of freedom system, then you will all come back to solving the whole bunch of single degrees of freedom system. You'd remember. So for this problem, even if I didn't cover much except the Friday last week, if you can solve single input, single output, you can do really well for multiple input, multiple output problems. And noise is just always just the following: input noise, output noise, things like that. So what we covered is this. For example, this is H, system. This is a system. This is H is always a function of F. And H tau, small h tau, this is H, capital H and the lowercase h. That's a Fourier transform pair. Okay, so to get the capital H, you have to take a Fourier transform of small h. To get back to capital H, then you have to take an inverse of Fourier transform. One way or another, this is the system. Usually the H is unknown, whichever H is, because it's a pair. And then this is a system. Then you deal with input, which is like input excitation shakers or impact hammers. So that's X, input excitations. For the data analysis, you just call the input usually. And of course, you have output. Output response. Okay. X and Y, input and output. And then what you did was you have pickup stations. I'm going to say that just to put this guy here, saying pickup input, pickup station. Usually put the circle with the summation sign. It's a collection point, the pickup point. So then I introduce like input noise. I always use MT, input noise, and have this is NT is output noise. So you know how to handle. You have to know how to handle that. You did, because we did always input, output, uncorrelated, correlated. The noise goes through the system. Noise is independent, doesn't go through the system, vice versa. And another kind we introduced was a feedback system, feedback loop, like a negative feedback. So here is I use usually B. Then you can designate the type of the feedback system as a white noise. Constant, okay? What does it mean, constant? In the frequency domain, it's like this. Okay, constant. That's a white noise spectrum. It's a flat. Could be 1, 2, 3, whatever, okay? So then this goes back to here. This is a negative. This is a positive. So we study this in 2 sections, 3 sections, vice versa. Last year I gave an example, the final exam problem without the feedback. You will see with the feedback this time. I have to make it slightly different problem, otherwise I can't give you the same problem. That's stupid, isn't it? So feedback. And in addition, I put the shaker here. Do you remember that? And this could be a known, for example. This could be known or unknown, things like that. So you have to. So this is about complicated. We have done it. Okay. So and as you see, for the multiple input, multiple input. I'm sorry, that's a single first Friday. What we cover, I'm gonna review this because I announced it. I'm gonna give you a problem. Now all the single input, single output were done. So now after lecturing Friday for an hour, for single input, multiple output, multiple input, single output. You handle it exactly the same way as a single input, single output. So what I'm going to do here is single input, multiple output. So single input is xt is right here. Multiple output, you have a multiple system. It has h1 equal to be h2 all the way through hn. Then this guy is all shared together, same input, and it's going to be all output. y1, y2, this is a whole bunch of the collection of whole bunch of single input, single output. This is 1, 2, all the way through the n. Another type, I'm going to talk more. Another type is multiple input. This is multiple input, single output. There would be another kind is multiple input, multiple output. Too complicated. That I don't have to do here. But if you know this, you can look into multiple input, multiple output. But this is like a multiple input. Multiple input, single okay, here, so this is like a transducer location. If there is a noise, I could introduce noise right here. Well, I just put the situation when you handle the noise very well. So I'll limit to chapter 4 for the final, but of course you will carry my notes in 1, 2, 3, then you have all the necessary equations set if you need. And if I go back a little bit, this area I covered the Friday, 5, 1, 2. This is somewhat useful, I mentioned. X is unmeasured input. It's ongoing, some natural input. Some motor is running just a little bit away from the system. Then X is unknown. It's ongoing, some natural input. You can't really measure it. And I is non-external input signal. This is measured. I is known. So you can excite the system using the non-source. Then try to get the H. Once you got the H, okay, of course Y you can measure it by the transducers. then you can determine you can approximately good estimate for X here. So look through this. I covered the Friday. Whoever couldn't come back on Friday, tomorrow is a good day to review. So that's what, read up to here. To here. And I skipped this, okay? You don't have to much worry. We covered the basic noise and the signal ratio, then you don't have to really time to review a few hours. You don't need that. But this, I want you to review this. This is a single degrees of freedom system. We covered very thoroughly in chapter 1, I believe. And this is at the beginning of the vibration course you covered. And it's something like, this is beginning. Okay, this is something like XT. This is MCK. This MCK system. You know about this, right? And you know H functions and all that. Whether I put on a side or vertical, is it same or different? That system is same as this system. That this system vibrates horizontally and is orthogonal to the direction of the gravity. But this is in the same direction of the gravity. Is it same? Is it different? The motion of X, Y or X, Y, this is different? And you're different? X expression gonna be different. When you put this horizontally, put this vertically. I'm pretty sure I mentioned about this on chapter 1. Youngbin, same or not? No, this is just a, I have a mass, I have a dashpot, I have a spring. Then I put the mass on it. This guy in a horizontal setup. Horizontal. The G is in vertical direction. I just put the mass, spring, dashpot right there. Then give a tap a little bit. Then it will vibrate. There, set up this way. I give a tap. Then it's vibrating. Okay, let's take a vote. Okay, this system is the same and no difference whatsoever. The response is going to be all the same between this and this. Raise your hand. You know what I'm saying? 이 두 시스템이 같을까? 그러면 틀릴까? 재범, 어때? 기분이 다를 것 같아? 성은이는? 내 눈치를 보니까 좀 다를 것 같아? 같을 것 같아? 그래. 종환이. 같을 것 같아? 내 연구실이 조금 낫다. 태민이. 마찰 없어요, 이게 없어요. 이게 같거든? 내가 너희들한테 챕터, vibration 챕터, 이게 beginning이거든? Did I give you chapter 1 of my vibration class? I don't teach vibration here. I think you have chapter 1, chapter 2, chapter 3. I think I gave you first 3 chapters. Take a look at, please. It's identical. Okay, it's identical. I'm not going to explain. You should explore for fun. Don't spend more than 10 minutes, or about 15 minutes. Okay. So here is the spring damper mass system. You know the frequency response function, right? Expression. How come you're not? It's so quiet. So that's the spring dashpot and damper and mass system. H. This H absolute, sometimes called what factor? Gain factor. You heard about it? I did. I talked a few times. Gain factor. What about the phi here? That's a phase factor. Gain factor. Magnitude. Amplitude. Gain factor. This is a phase factor. I'm going to ask you find expression for gain factor. Find expression for phase factor. You understand what that means? What's FR? This is review for Friday students. FR, resonant frequency. Resonant frequency is equal to the natural frequency. Yes or no? No. Gusto. The resonant frequency is not the same as the natural frequency. Why? When resonant frequency is same as natural frequency? When? If there is no damping, it's identical. If there is a damping in the system, then resonant frequencies shift. Here, if zeta is equal to 0, identical. Fr is equal to Fn. Otherwise, okay. Magnitude, phase. You have to review all this. The Friday lecture. Don't feel I'll do it next week. Too late. This is multiple input and single output. First, to take a snapshot in your brain. Remember, x1 all the way to xq, h1, h2, hq. This is v1, v2, vq, pickup station, God bless you, and y, output, okay? There's a whole bunch of, if you look at this is one case, another case, whole bunch of single input, single output, no difference whatsoever. At this moment, this equation set should be very familiar to you. Nothing to be strange here. Why? Summation of capital VI, right? VI is HI XI. It clicks your heart. Y star Y. Y star VI star VJ. Then VI is HI XI. If it's a star, you have to put Vj. So this is that. Or you can have just a slightly different expression. Same thing. And remember, not memorize anything. You should click all really well. How many of you, someone was here Friday, right? Yeah. Jevon, did you have a chance to look at the Friday notes? No. Are you willing to look at the Friday note today? Oh, tomorrow, by tomorrow. If you don't, you lose. I'm telling you. So, Tamin, did you have a chance to look at Friday's note? Okay. Gusto, did you? Did you review the Friday's note? You didn't. When? But you have a Friday, Saturday, Sunday. Who said there is no class? No class Friday? Who said no class Friday? No, he was here. Hey, Gusto, go back, read whatever I cover on Friday, all the way to the end, okay? Yeah. Otherwise, on Wednesday exam time, you have problems. And this is a single input, multiple output. Single input, right? And multiple output. If there is a noise, I can introduce noise right at the collection point if I want to. This whole thing, this is a one set. So I told in class Friday, understand this, how many percent? Jusung? How many percent I said understand all these equations for? 1000%. Did I say that, Chora? Yes. Look at this diagram. Take a look at the expression for yi is equal to that. What relation, this relation, what do you call? Someone, what do you call this relation? Convolution integral. In Fourier transform domain, yi is equal to hi times x, right? X is one single input. Then you, from here, you apply, take the expected value in both sides. Then you have, this is mean value of x times integration of hi. Unit impulse response function of hi. Okay. Then if you look at chapter 4, section A. If you look at the page, second page, you have autocorrelation is equal to this. Is all derivations is all out there. Do I have to memorize? Don't ever memorize. So if you open the note, it's all there. So nothing to memorize. If you take a Fourier transform of R, Y, what do you get? Tell me. If you take a Fourier transform, R, Y, the result, if you take a Fourier transform of R, Y, what do you get? 서로. Power? Power what? 주성, what do you get? Auto spectra of Y. RYI difference is rather than Y is YI for multiple output. Same thing, no differences. This is a system-dependent parameters. GYI is equal to HI absolute square GXX. I just put the I. If it's no I there, so GYY is H absolute square GXX. I just depict the one row. RXYI is the relation between input X and YI. It's ith system. Very systematic, right? GXYI, HI, GXX. So, single input, multiple output. So R, YI, YJ. This is relation between the ith system and jth system. Then you say let t minus alpha is y prime, then you can rearrange it. Then you can re-express like this. GYI, YJ, this is YI, YJ, this. This is coherence function between the output YI and YJ. Coherence function, whether it's related or not between YI and YJ system. Identical, if you drop the I and J, that's what you see all the time. And this is equal to 1. Do you need all this relationship? You expect that's equal to 1. Why? Youngyu, why? No noise. No noise is ideal system. If it's ideal system, it's 1. Okay. If it's not the ideal system, then of course you expect the value is less than 1. And YI is HI, XI, X, YJ, star, star, star. This is multiplication, GY, IY, J. This is a quick review, but whoever didn't have a chance to review, but don't worry, you have a chance to do today, tomorrow. This is one of the experiments done not by Bandit, maybe some university. I didn't ask Bandit, but a very simple fixture. And we have in the lab very simple like this, but we put that in the vertical. It shake in the horizontally. We have a deck plate. Then it's a base. You saw that, right? You use it. You used it already. So this is like, then you have a shaker attached. The motion is in that direction. This roller is over there. Then this is a deck. This is a mass there. This acts as a spring. And this could be the damper, something like this. Do you see damper? Do you see damper? Say no. There's no damper. Then how can I say damper? Damper usually coming from the system. Coming from the system, if you look at there is a screw right there, screw. Then you can really roll the screw, then tightening up the rod, then there should be no slip there. But still there is a frictions and all that. That friction generates energy loss. Whenever the energy loss happening at the joint, then what happens is damping there. Damping means energy dissipation. Where the energy dissipates, mostly right at the joint. And this rod also, through the rod, the motion, energy dissipate. That's material damping, which is very, very small. You can neglect it. So this is identical to this. And you have also, if you look at there, you have accelerometer. 가속도기 is right here. And you have a 가속도기 is right there. And here is a shaker generate the motion. Identical, no differences. Okay? But here, this is like a GXX, and whenever you have a peak here, there are a lot of noise in here, high frequency noise. But here is a peak, then I've got to know whether this is a mode or not. Mode related to the peak here in the GXX. So GXX is this input excitation, sorry, this is input. It generates the input motion. Okay? So let's just let it just say that this is GXX is input. And this guy is a coherence function, and this guy is a gamma xy square. It's almost all nicely close to 1, except the high frequency. High frequency noise could come in. And here, this is a GYY, is output. As output has a peak here and peak here. Then question is it really mode? Well, if you plot the H absolute, which is transfer function, the gain factor, so this is a peak there, around there. As you look at around here, this is GYY is relatively close to the shape of H absolute. So if you look at here, it's very close here, which is about 100. This is about 200, which is very close to here. So this kind of the experiment, you have done it with the Higgs, but this is this. Well, at least you exercised this time, and this is phase factor. Phase factor, right at the modal frequency, it has 180-degree jump. And right here is another jump, right at that frequency. Look like it is modal frequency. You heard about the modal frequency in vibration? I think some of you took the vibration class. 정말, you took the vibration class. This is another experiment. We made this plate this time, but didn't have a chance to show you. And next year, if we have enough students, we're gonna have a chance to do this. Okay. So I gave you the. I narrowed down quite a bit what to prepare. You have only today and tomorrow. So I think that would be the best. You have to know H, right? Summary of summary. You have to know H. Just all you need to bring here in the class for on Wednesday is my notes. That's all you need. If you bring more, go ahead and bring more. It's gonna confuse you more. This is, you have to know as H, right? Very clear. And as I mentioned, single input, single output stuff, you have to know 100%. Review what I covered in chapter 4, even turn the page where the information is. And take a look at how to handle the noise, input noise, output noise. That's about it. Then feedback loop. We have this. We have done so many times. So this is like a B. Review that. Review that. Noise. Noise there. I always use noise as a 1. Noise is N. This is noise is N. What else I can do? Multiple input, multiple input, single output, single input, multiple output, few page. You have to review that. I'm giving you a problem set, which has all the basics we learned. Question now.